He is going to talk about unexpected efficiency of Newton's method.
Thank you very much. Of course, I'd like to thank the organizers for inviting me here, not only today, but over the past, well, almost 25 years. In my case, it's only 24 years that I have been here. It started with this memorable conference celebrating Jack's 60th birthday, wonderful conference, and since then I've had many beautiful and nice returns here. So thank you for all these invitations and opportunities, and for the opportunity of meeting nice people that initially were just authors of books or papers. Many of them have become friends meanwhile and good colleagues. It's been a very good time. Okay, when choosing the title of the talk, I thought I speak about something which has been with me for almost the same period of time. I have been working on Newton's method for decades in the plural. Still, if you think, like with Araceli's talk, if you think you've seen the talk, I don't think you have. Some of the results are just a few days old. And so the unexpectedly efficient part, that is something I would have never assumed long ago. So this is the talk with as much history as it gets. Newton was a person and he invented Newton's method, so as old as it gets, you know. You have a differential map, how do you find the zeros? How can you approximate it? And you iterate this, so I have a wonderful pointer here, but you all know this iteration function here. The Newton method, which is just a tangent to the graph and find the zeros of the linearization at some point, and then you iterate that. It's well known locally, it's extremely fast, so once you're near a root, then you will, at least if the root is simple, converge quadratically. That means the number of valid digits doubles in every iteration step. Perfect, you would say. It's easy to implement. It's very robust. It's a hyperbolic dynamical system. Usually it's stable under perturbations. And you can run it in parallel. So it's the perfect method, at least locally. But when you look at textbooks, they say don't use Newton's method because globally it's poorly understood. It behaves chaotically. Well, but chaos is not something that scares us, right? That's our business. So we just have to get control over Newton's method. And here are some pictures that presumably you have all seen many times. But just as a reminder, you can extend the Newton method, of course, over the complex numbers. And then if P is a polynomial, you iterate a rational map. So you can ask, why do you want to iterate polynomials? But the Newton method wants to be iterated. It's made for iteration. And, well, you know, it gets good pictures. There's the old paper by Cayley, I think 1876, that's trying to explain which starting points in the complex plane on the Newton method will converge to which root. And he has a solution in degree 2. If you have a quadratic polynomial, here are the two zeros. Then you draw the bisecting line. Everything on this line converges to one root, everything on that line to the other. Nothing could be simpler. And he said an analogous paper on the cubic case will be forthcoming. So far, it has not come forth, as far as I know. And of course, you know why this is the case. So here's degree 7, with 7 different colors in the complex plane. The coloring tells you which starting points converge to which of the roots. So there is a blue root here. Well, the roots are thick white dots, and all the blue points converge to this root. And there are many more blue dots here, which all converge to the same root. And then there's red, and so on. So that's the complex case. And even in the real, when you said, OK, the iteration over the real should be very simple, here is a degree 10 real polynomial. And I had a number of roots nearby here and a number of roots nearby there. And now it's hard to tell just by looking nearby, when it just barely oscillates over the reals, how many roots are next to each other. Well, you know my favorite saying, real mathematics is difficult, complex mathematics is beautiful. So out here, the real roots, well, there's a blue, yellow, light blue, and a purple root, so there must be 4 of them next to each other. So even if it's a real question with a real answer, this might actually help in the complex setting, in the real setting. Okay, but, well, as we said, life isn't so easy, or I wouldn't be giving this talk. There are some problems. For instance, you can have bad starting points that when you're near a critical point of the map, you will zoom off to infinity. And then you're far away. You might recover, but it might take a long time. Or you might lose control altogether. And then there are basin boundaries. When you're on the boundary of one of the basins, you will remain on the boundaries. And as we all know, the boundaries may have positive measure. Xavier and Arnaud are, it's their fault. So that when you're on the boundary, you can be unlucky with positive probability. But much worse yet, there are as innocent polynomials as this cubic polynomial with integer coefficients, for which I've drawn the basin here. You see the red root, the green, and the blue. And many points converge as they should to one of the three roots. But if you look carefully, you see a black dot here, and there's more black there and there and there. And this black corresponds to superattracting two cycles. So from the dynamical systems point of view, it's wonderful, it's stable under perturbation and everything. Only it's not, from root finding, so there are open sets of points that will not find you any roots. So indeed, the global dynamics is hard to control, it's chaotic. But even if we knew that almost every starting point converged to some of the roots, we want to find all the roots. And we want to do that without deflation. Just in one shot, find the roots all the time. And for polynomials, in the end, I'll talk about polynomials degree 1,000,000 and higher. Of course, we did this with systematic computer experiments. I thought, you were the native speaker, so maybe using the wrong word. When you divide out, you find some roots, and then you divide out the roots that you have found. What is the English teaching? What's the proper word to use? You have a polynomial of big degree, you find some roots, divide it out, and you get a polynomial of lower degree.
Well, isn't there an official term for this in the trade?
Yes,
It's called deflation.
Yeah, okay, that's what we teach our calculus students to do this. Maybe you're lucky you don't have to teach calculus, but that's okay. Okay, but so thank you, Scott, for rescuing me here. Okay, and now I'm very happy to say, let me make a historical remark. When I started this business, I wanted to understand the dynamics of Newton's method. I never intended to have an efficient algorithm. But so this is a new bit, this is a historical remark. Now we want it to be efficient. And now we want it, in fact, well, it's unexpected, but still it will be in the end. So those of you who stay awake till the end of the talk will see that it's really good, even for high degree polynomials. So let me start with some old news from 2001. And the paper was actually written during one of my stays here in Stony Brook for a semester. Scott, you're around? I heard your voice over there, yes. So it goes back to his thesis, in fact. And John Hubbard was involved, who's on his way here. He convinced me to talk about this topic, but he's had to give a talk this morning in Cornell. Should be on his way now. So the old news. We fix the degree of polynomials. PD is the space of all complex polynomials. Degree is fixed, and then we scale coordinates so that all the roots are in the unit disk. It's not a loss of generality. You just have to have some bound on where the roots are. So, given the degree, then there is an explicit and finite universal set SD of starting points, so that for every polynomial of this degree and every root of this polynomial, at least some of these finite many starting points will converge on the Newton method and find this root. And that set can be quite small. So if you want to find d roots, you have to have at least d points, obviously. Then there's a fudge factor of log d squared times an explicit constant 1.1, which isn't very big. So that thought, and if all the roots are reals, then indeed 30% more starting points than roots suffice. So that's, except for a constant, best possible. So that's old news, as I said. At the time, we were proud. It was the first paper in which Invention is printed with color pictures. In fact, before we received the referee report, which was favorable, they asked us about how to print color pictures in the journal. So we took this as a good signal. Okay, I'll show you a picture in a moment on how to place these. It's not just an existence of such a set, it's explicit, you can write it down. It's an easy set. And we thought this is best possible until Bela Bolobash came along and told us, well, if you don't do this deterministically, but have a random element, then you can replace the log d by a log d squared. So it's even much better. And as we all learned in calculus, at least those of us who teach it, log d goes to infinity, but it has never been observed doing so in practice.
So what is it, the constant depends on your threshold for acceptance or something?
Exactly. I mean, there's a certain probability, and depending on the probability they want to achieve, you get a different constant, which depends on the probability, but not on the degree, obviously. So here are the starting points, and the credit for the picture goes to our friend on the back there. You made this, I don't know when, 20 years ago, or 18 or 17 or whatever. So this is a friendly polynomial of degree 50, for which you have 47 roots on the unit circle here. You see the red dots, and yellow is the starting points that converge to these respective roots. And then we have 3 more roots which get individual color, red, green, and blue. And you see the colored basins. Well, from this circle around the roots, you can reach, and you could ask if you have roots here well hidden by a big circle of many roots, can you see these roots from circles around? The answer is yes, you can. But of course, these channels are pretty narrow here, the blue ones, for instance. And there is a blow up. So you see there are 2 circles of starting points, and each of them has a regularly spaced set of starting points. And the blue channels are being hit by the starting points, but just barely, so we don't have very much to give away there. So as far as the deterministic bound is concerned, it's near optimal. You may also see here light green, light gray. So the gray open sets are starting points that don't converge anywhere. Well, they do converge to attracting cycles, but again, with positive probability here, you're not going to find any root. So I hear some questions there. No, there aren't any.
Means when points of extent 0, but maybe what you meant is are there 2 bands of them or something?
Yeah, it's really.
Is that what you meant by scale? Is that just some shape?
Yeah, I mean that's because there was discussion between Scott and me at the time. So I had just manually drawn some pictures of starting points where they actually went, and then he complained, but the actual set of starting point has different constants. So this is exactly the constant that we get from the paper. So it's what is it? 0.2667 log d circles, which 4.19 d log d points on each of them. And if you multiply the 2 constants, you should get 1.1. But my memory over those years is a bit faint. Whatever, the numbers can be made explicit. It's not just there exist some numbers, there are very explicit numbers that you can write there. Okay, so this is the prehistory of the beginning of my time here in Stony Brook, so to speak. And then the question obviously remains, how long does it take? I mean, so in principle, we can solve it. But you know, mathematicians have a reputation of preferring to build firehouses rather than put out a fire. And so I'm trying to engage in putting out fires, if that's, well, root finding is almost as important as putting out fire, right? So how long does it take? And that again, as you see, has a long history from 2002 to, well, 2014 for this page, and later it's more like last few weeks. So the first statement is the same result as we had before, but fixing the variables. You fix the degree, you fix the desired accuracy epsilon, then there's an MD, which is the number of iterations, which will depend only on D. So that for every polynomial and every root, one of the starting points from the universal set will converge to the root under the Newton map. So far, we had this before. And now Zj after mj, little mj iterations, is a distance alpha j less than epsilon. So that means the orbit is epsilon close to the root. Little mj is the number of iterations you needed, and the sum of all those for the roots is bounded by big MD. So the first sentence really is a definition of MD. The total number of iterations are required starting at this small universal set in order to find all the roots. And now this total number MD is, in the worst case at most, d to the 4 plus d log epsilon. That's when you have multiple roots. And in the expected case, you can really give a precise average. Then it's d squared times log to the 4th power of log d plus d log epsilon. And this log epsilon is really the quadratic convergence. And then this is the leading order of what it takes. When you look at it more precisely, you will see that
has natural value, or is that an old number?
there may be, I think there should be an absolute value, you're right. Again, from calculus, there's some rules which you can use to convert those. Yeah, but it is true. So this is linear convergence and this is quadratic convergence here. In practice, this doesn't matter because, so this is once you have separated the roots, these things take over. So the real interesting terms are those, and they are much bigger than the epsilon terms. So the complexity really does not depend on epsilon, unless epsilon is 10 to the negative 100,000 or so. I mean, log 100,000 isn't a big number still. So these things are what matters. And then the big O you'll see in the end is not just some constant. We made experiments, and the constant is like 4 log 2 or so. So it's a very modest constant, and not just up to a gigantic number. The last result, let me advertise some of my students, is the bachelor thesis of one of our Jacobs undergraduates, Todor Bilarev, and the paper is about to appear in Mathematics of Computation. We just received the page proofs last week. So this is very recent. And I also want to point out this is essentially the best possible result when you have starting points outside of the unit disk. Because in order for the machinery to work, you have to start at a definite distance from the unit disk away. And then iterate towards the unit disk. Every point has to iterate a constant, a number of iterations that's proportional to d. And you have at least d starting points. So in order to get to where the action takes place, you need d squared iterations before something happens.
Did you say what your space PD was? So it's
Yes,
normalized?
I'm not sure whether I said it, but I showed it here. The space of all complex polynomials of degree d normalized so that we have all the roots in the unit disk. Yes, and this is always, for the whole talk, the convention we will use. Okay, so we have to start somewhere at a safe distance from the unit disk in order to have some precise estimates. And that needs approximately a constant times d iterations times d points. So you need d squared iterations to get into the action. And that's the limit for this part of the method. Okay, so let me make a little detour on the, yes?
Can I ask really briefly about the previous slide? So the comment under the theorem, when you're saying low time complexity.
Yes.
So the steps for you is just one iteration of Newton's method, right? So you take that as a time unit.
Yes. And then you can ask, how expensive is that one? And then you could say, well, are we hiding a factor of d in evaluating the Newton method step? In principle, yes. In practice, depending on how efficiently you can evaluate the polynomials, but even if you know them just by coefficients, then since there are many points to evaluate, you have d points for a degree d polynomial, and they get evaluated not in d squared units, but some d times some log factors. So if you want to have the arithmetic complexity, it is higher, but only by a log factor. So it is a difference, but not a huge one. Okay, so Newton's method is a dynamical system. There is this picture, I showed it before. We have a super attracting 2 cycle here. And it was known for a long time that such cases exist. I thought they were discovered once the first computer experiments were made. But last Thursday I was speaking in Victor Pan's seminar in New York, and Michael Schub was there. He tells me, no, Steve Smale observed it, or he predicted it just from first principles without having seen it on the computer, and then constructed with pencil and paper examples where you would have super attracting cycles of higher periods. So he knew this even before the computer pictures. And he asked the question, can you classify all polynomials for which the Newton map has attracting cycles of higher periods? Before giving the answer, let me show you the simplest non-trivial case. As I said, the quadratic case is boring, so the interesting case is cubic, space of all cubic polynomials. So this is parameter space, and we parameterize essentially as follows. I'm lying slightly. You choose coordinates for the three roots so that the first root is at the origin, just by translation. Then by scaling complex coordinates, the second root is at 1, and the third root is wherever it is. So the polynomial takes this from z times z minus 1 times z minus lambda for a complex parameter lambda. You might say there's a leading coefficient in front of the p, but Newton's method p over p prime, that cancels away. So that is irrelevant. And really we have a one-dimensional complex parameter space, and here it is. Now, if there exists an attracting cycle of higher period, then some critical point will converge to it. Well, we have, for degree 3 rational map, we have 4 critical points. 3 are at the roots, and the fourth is the free critical point, which is the center of gravity of the 3 roots. So we color the complex plane by the behavior of the free critical point. Most likely it will converge to the red or the blue or the green root, and then we color the point and parameter space accordingly. But there's a small blow up here, which you see there. So there are some black points which do not converge to it. So the black points are the parameters for which the critical orb is attracted to a higher period cycle, more precisely the closure thereof. And then there's another blow up here, and well, I don't think anyone here will be much surprised to see that this is the Mandelbrot set. So when I said earlier, Newton maps want to be iterated, in order to understand the interesting cases of Newton maps, you must understand the dynamics of quadratic polynomials. And so quadratic polynomials want to be iterated too. So there was a little commercial which was not surprising to people here in the audience. So let me add another commercial on one of my former students and one of my current postdocs. So we have a classification of all post-critically finite Newton maps. If you look at them not just as a root finder, but as a dynamical system, iterations of rational maps, there are some interesting properties that combinatorics of rational maps is notoriously difficult to find invariant combinatorics. We are working on it. Many people are working on it. But the Newton maps are ones for which you have good combinatorics because they have immediate basins, they touch all at infinity, and they help to understand the dynamics. So he has a classification of all post-critically finite Newton maps of all degrees. And of course, if you classify them all, in particular, there's a classification of all those that have cycles of higher period. So a special case is an answer to Smale's question. So this is the second class of rational maps of high degrees for which we have a dynamical classification. Polynomials we understand well. Alfredo is there. He did this also in the old days of Stony Brook, part of the history of the Institute. And now Newton maps are a family almost the same degree as polynomials, or the same dimension. Within the space of rational maps, Newton maps have about the same dimension as polynomials, for which we have a classification of all, at least all the post-critically finite maps. This classification is in terms of finite graphs. You take the immediate basins from the root. You can connect, I'll show the pictures in a moment, you can connect the roots all to infinity through the attracting basins. That gives you a graph. Then you take a pre-image graph, and a finite pre-image produces a connected graph that is part of the classification. And then the complementary domains might be polynomial-like maps, and then you can get all kinds of dynamics from polynomials embedded in it. So this project has been completed quite recently with Russell Lodge, Kevin's former student who is now postdoc at Jacobs. And we discovered there's a nice result, a nice corollary, which I would like to share with you. We all know the Fatouche-Shikura inequality, so that the number of non-repelling cycles is bounded by the number of critical orbits. But that, in fact, can be made more local, saying that every non-repelling cycle has its own critical orbit. It was known for polynomials. It's true as a corollary also for Newton maps. And you can ask the question, maybe this is true in general. For rational maps or beyond, does every non-repelling cycle have its own critical orbit, just rather than just counting the total numbers? So let's see, at least here for this family of maps, it works. Yeah, and that goes back, exactly, Kiwi was involved, goes back to an old paper by Lisa Goldbeck and Jack Milner when they have the orbit portraits. That's what you start for polynomials. And then I think Kiwi was the one who observed, or at least put up the idea that it could be separated from polynomials. And then what you do here is the roots are attracting fixed points. They eat their own critical points anyway, critical orbits. And all the other cycles are in polynomial-like maps and inherited from there. It's not a big result once you have an understanding.
This essentially includes a reduction to the polynomial. It's not just analogous, but it actually really uses them.
The work is in understanding Newton maps and giving the classification. And once you know that you understand the dynamics, then you just observe. I mean, it's just a recent observation. It's really polynomials plus observing there are d roots which eat the orbit. Nothing new really once you have a classification of the rational maps. Of course, that's where the work sits. Okay, so I want to get back to the unexpectedly efficient root finder. And perhaps here going back, so this was a result of between 2002 and 2014. I've been working on this for a while. In 2002, in fact, even earlier, but that was published in 2002, I had the first bound that the number of iterations that you need has an upper bound depending only on the degree and nothing else. I was very proud of it, that there's an explicit bound, but unfortunately it was exponential in D. Well, I figured this is the best possible you can have. And then I was invited in 2006 in Toronto to Mike Shoup's seminar in complexity in dynamical systems. And well, I was proud to be invited, but I was embarrassed at the same time. The complexity theorists invite you, and you give them an exponential result when it should be polynomial. So I spent a couple of nights before trying to find arguments why better than exponential was unlikely, trying to justify it wasn't as bad as it looked like. And every time I thought I had a convincing reason why better than exponential wouldn't work, I realized, well, yes, but you could say this. And then I tried again, so I was arguing with me quite a bit. And in the end, it turned out in 2006, after all, you could do it in polynomial time. So that was the 2006 thing, and then there was some degree d to the 6 or so in 2011. It was down and down and down until Toto came by and made it the best possible thing of d squared. So let me show you the same picture again, to introduce some notation and some ideas I want to show you. At the end of the day, it's embarrassingly simple. It's not the deepest result I ever had. And I'm trying to give you a more or less complete proof, at least for a weaker version of the result. So we have the 7 roots here. Every root has a basin, the open set of starting points that converge to the root. And the immediate basin is the connected component that contains the root. So this is the blue immediate basin, and these blue dots are part of the basin, but not the immediate basin. And an old result of Felix Przyczynski, 84, I think, is that every immediate basin is simply connected and has infinity as an accessible boundary point. So there are no islands within the immediate basin. You see it goes to infinity. You see infinity there and there. Actually, I can go all the way back. No. Here, that's the same picture on the Riemann sphere. Here you see the point at infinity. And you see one blue channel, and then there's another blue channel coming in from the back. They're separating, surrounding the purple. Green has one channel here and another narrow channel here, and a third one coming from the back. Then the 2 red channels, and so on. And so that's exactly the same picture, but the Riemann sphere view. Okay, so this is the corresponding definitions. Immediate basin are defined. Przyczynski's theorem I mentioned. The channel is an unbounded connected component of the immediate basin minus the closed disk. It's just the part in the immediate basin that goes to infinity. And within every immediate basin, let me go back, you define the quotient of the channel. We want to measure how wide the channel is. Obviously, a thick channel like this green one is better than a thin one for the circle of points around here. This one is easier to hit than this one. And for that, we need a measure of of the width of the channel. And we measure it by the quotient of the channel by the dynamics. So you have, so somebody will complain about the light, but I hope it's going to be okay. So this is a big circle which maps to the next circle under the Newton map. This is part of the immediate base, and then you identify the two boundaries, and the quotient of this is just a cylinder. Every conformal cylinder has a modulus, and that modulus is the width of the cylinder. Roughly speaking, if you imagine this as a rectangle, it's the ratio of the height divided by the width of this rectangle here. And the wider it is, the bigger the modulus is. And then one of the theorems that we had with Scott and Hamill in the old paper is that every root has a channel with modulus at least pi over log d. And then we're using, within the immediate basin, the hyperbolic metric, and the geodesic connecting all the way around here. The length of hyperbolic metric normalized to curvature -1 or whatever, then the length of this closed geodesic or connecting those points. That means there is a point from here, the image. This line has length at most inverse of the modulus, which is log d. So the bottom line is that at least when you have a starting point near the center of the annulus, then the hyperbolic distance along the orbit is bounded by log d. So there's an upper bound on how much you move in the hyperbolic metric. And since the hyperbolic metric is always contracted, if you have an upper bound here, then along the iteration, the upper bound will only get better. So now one of the problems is when you iterate and you get close to the center, you might fly far away and lose control under the iteration. And I have the concept in our central orbit for which it doesn't happen. It is known when you're outside of the unit disk, you will move at controlled speed towards the unit disk. So away from the disk, there is no problem. You get better and better towards the origin. But on the disk, anything might happen. And I call an orbit R central. Zn is the orbit. So n plus 1 is image of Zn. An orbit is R central is whenever you're within the unit disk, then the image is at distance at most R from the origin. And then again, you get closer, 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 closer to the origin, and never. So the whole orbit is in a disk of radius r. It's a big disk, but it has bounded area. And then one of the first observations is, if you are in the immediate basin and you're in somewhere in the middle, so if this is the channel here of the root and you're in the middle third, like so, then the orbit, you start here, the orbit is R central for some universal value of R. So you'll never get too far away when you start in the middle third. So once you have that, then finding good starting points is easy. We have this old result that tells us how many starting points we need in order to be in the immediate basin. Well, now we pretend our immediate basin is just the middle third of this. We need about 3 times as many starting points. And then we know we are central, so we can never escape too far. So why is that so? We have an upper bound of log d, distance of the hyperbolic metric between Zn and Zn plus 1 is bounded by log d, so you can't move too far away. And now, or perhaps when you're in middle third, there may be a factor of 3 because it's a bit wider, whatever. So it's the bounded distance. So when you iterate towards the unit disk, then you have only one iteration to get away, because once you're away, you have to get back to the unit disk. And with bounded hyperbolic distance, you just can't get too far away from the unit disk. So it's a simple observation using a hyperbolic metric, but that gives you an explicit way to find starting points that have R central orbits, which will not escape too far over time. So some equally elementary facts for Newton method, which just involves the logarithmic derivative. Zn to Zn plus 1 is the Euclidean distance that you move along the Newton step. If you move some distance s, Euclidean distance, then some root has distance to the orbit at most d times s. D was the degree. So when you move very slowly under the Newton map, that means some root is nearby. And second thing is, if the distance to one root is smaller than distance to all the other roots by a factor of 2d approximately, that means you're, by a big factor, closer to one root than to the others, then you're in the domain of quadratic convergence. So then you found the roots. From here on, you will converge to the root, and the number of digits will double in every step. So then you can essentially stop the iteration, except for very few iterations, essentially log epsilon iterations. So the third observation, if we put the roots randomly in the disk, then the mutual distance between roots is at least 1 or d, or perhaps 1 over a power of d. And if you throw the coefficients randomly within some distribution, then the roots tend to accumulate near the boundary of the disk. So they're a bit closer to each other, but it's still something like 1 over d squared or so. So under essentially any sort of randomness assumption or expected value assumption, there's a polynomial bound that roots are unlikely to be too close to each other. Let me stick to the first case, that we have mutual distance 1 over d between nearby roots. So we iterate along the orbit, and if at some point we move less than 1 over 2d squared, then by the first observation, there is some root at distance d times that, so at most 1 over 2d squared from your orbit. But since the mutual distance between the roots is 1 over d, which is much bigger, that means we really converge quickly to this root. And so we have quadratic convergence, and we only need to iterate log epsilon more iterations. So that means we really only have to estimate those iterations which have an upper bound, we have to have a lower bound on the Euclidean distance. Once there's an upper bound here, then we're essentially through. So we only need to iterate while the Newton method really changes the Euclidean distance along the orbit. So we have a lower bound on the Euclidean distance, and remember we have an upper bound on the hyperbolic distance along the orbit. So now I want to talk about using up area within this big disk of radius r. So we have starting points from our universal set, which are in the middle of the central subannulus, so that the hyperbolic distance is at most log d up to factors, and the Euclidean distance is at most 1 over 2d cubed. So hyperbolic distance is essentially Euclidean distance divided by Euclidean distance to the boundary. So the distance, if I have a point and its image, and I connect this by a curve which is long in the Euclidean sense and short in the hyperbolic sense, then it must be Euclidean far away from the boundary. More precisely, distance to the boundary, roughly speaking, is, so what is it? Euclidean length divided by hyperbolic length. Euclidean length is this divided by hyperbolic length. So this curve here has distance to the boundary at least 1 over d cubed times log d. In other words, if you have an orbit in the immediate basin, go from here to here, then this whole curve has to be far from the boundaries that can connect them by something like a thick line. So, thick line, how much area am I using here for this rectangle? Area, we learned this in calculus 2, is length times width. The length is 1 over d cubed, the width is this thing, so the area is the product, is 1 over d to the 6 log d. All these areas are in the immediate basin. We measured the distance to the boundary. So different roots use different areas. And moreover, as you iterate here, are these areas all disjoint? Well, maybe not quite, but only log d of them can overlap. So you have to throw in another factor of log d for the overlap, and that means an area available was pi times r squared, calculus, and area per iteration is this, so the total number is this. So the total number of iterations is d to the 6 times log squared d that you can have just by estimating the area available. So that is some bound. That's essentially the idea of 2006. Now I claim d squared is better. I'm not sure I want to get into all the details. If somebody wants to see the details, they are there. The fundamental idea for the improvement is that when you are, so we use a lot of area if the Newton step is big, if we jump a lot. So the best bounds happen when we jump a lot, but jumping a lot means we are far from the roots. So the only places where we don't use much area is when we're near some root. But being near a root, there are only small areas near the roots. So most of the time you're away from the roots, and then you jump much, and then you use more area. So you just make a fine play depending on how far you are from the root, and then just subdivide the plane here into the set of points so that the nearest root has distance essentially 2 to the negative k. And then make the separate estimates depending on how far you are from the nearest root. And then you get d cubed times the log term. And then with some more clever estimates by Todor, it's d squared after all. And every time you kill a d factor, you gain a log d. So that's the result of 2014, which is just coming out. So that's the theorem. Reminder, when you all know the trick, you announce a wonderful theorem, and then you entertain the people for a half hour with all kinds of details until everybody's forgotten what you wanted to prove, and then something very different. So let me see whether it's still the same result from the same years as before. You fix the degree and the accuracy, and then MD is the total number of iterations you need for all the starting points until you get epsilon close for all the roots. And then this total number is at most d to the 4 plus d log epsilon in the worst case. Well, in the worst case, I showed you a d to the 6th estimate, but still, and in the expected case, it's more like this. Okay, and now Misha Jampolsky asked the question about the unit of measurement. So there's a comment here, but I answered that question earlier. So that was the theory. And now I want to say something about practice. And perhaps we should have tried to make estimates ahead of time to see how long it really takes. But we did this after we had the result on the upper bound. We figured, so how far is it from reality? And then, yes, somebody's taking pictures here. So you see the picture of Robin Stoll. He will come up. This is Robin Stoll, an 18-year-old first-year student. I was a high school student when we started this. Robin cannot be here. His father is here and takes pictures. He wrote a program, various programs, and with the ambitious goal, let's do it in practice for polynomials of degree 1,000,000 or more. So find all roots of various polynomials of degree 1,000,000 or higher. So there are 3 or 4 different polynomials we are working on. First is you look at periodic points of z squared plus c. For c, we took 2 values, I and 2. And then periodic points of period 20 give us a polynomial of degree 2 to the 20, which is bigger than 1,000,000. The second, well, this is a pair of polynomials. The next one is you take centers of hyperbolic components of the Mandelbrot set. So this is just c squared plus c, squared plus c, quantity squared plus c, and so on. Then they have, if you do this n times, you have degree 2 to the n minus 1. So for n equal to 21, it will still be 1,000,000. And since it was so successful for both of them, then we figured people might complain, yeah, these are very specifically designed polynomials. And what in general? Well, then we took just a random composition of 20 quadratic polynomials, which had no property other than being easy to evaluate. You could say, why not just take polynomials in terms of coefficients? Are these random? Well, we wanted them to be evaluable by iteration because that's much faster. And if you evaluate them just in terms of coefficients, it takes a lot of time, and then the high-speed algorithms, in which we didn't want to get involved with. with. We just wanted to have a cheap oracle that evaluates the polynomials for us without messy details of coefficients. But we believe that our polynomials have no special properties other than being easy to evaluate. Here's another reason. And that's why we chose c equal to 2 here. We had a referee in a paper that was eventually evaluated. He complained, or she, I don't know, that it makes no sense to have a distribution over where the roots are, because if you know the roots already, then why look for them, right? Well, still you can have the distribution of roots without knowing where they are specifically. So it was a specific request. We had to do it in terms of known coefficients. So here's my counterexample. For z squared plus 2, you take the 20th iterate and look at the constant coefficient. That is 2 squared plus 2 squared plus 2 squared plus 2. So it's far bigger than 2 to the 2 to the 20th. So even the constant coefficient is gigantic and wouldn't fit into any computer. So this polynomial here, the 20th iterate, the coefficients you cannot store. So you couldn't even, if you can't even store the coefficient, there's no way of evaluating the polynomial. But nonetheless, the roots are somewhere in the unit disk, or this of radius 2, and we found them easily. So coefficients are not necessarily the right condition to use. As I said, sometimes we cannot do it. So now comes the story on my friend Robin. For all these polynomials, all the roots were found, and not just by fancy high-speed clusters, essentially in the end on his laptop, which isn't a very recent model after all. So he would have liked to have an argument, of course, to say, well, I need a better computer, Daddy, can you buy me one? But that didn't work. So the first time we did this, December 14, as I said, it's recent. It took 35 days or so, in fact, on the university computers until the degree 1,000,000 polynomial was factorized completely. And then he realized he could improve the algorithm. Then it was just a bit more than a day in February. And in March, it was just a matter of minutes to find routinely all roots of these polynomials. And there's some results, but some results that we can prove and some observations that we cannot yet prove. And this is what I want to share with you in the end. So when you have a large class of polynomials of degree d, including all the above, you have the unit disk that contains all the roots. And then you start with the starting points on radius, say, 2, constant factor away from the unit disk. And then you iterate all those points. And when you have enough points equidistributed, you will find all the roots. We know this. And the average number of iterations it will take is log 2 times d plus log epsilon. Average over all the points on this starting points. Counting only those that do converge to the roots. There may be some that find higher order cycles, and of course they would contribute infinity. You ignore those. It's a bit mysterious. You would expect this should depend somehow on the polynomial. And well, but whatever we thought, I can show you pictures, what it should depend on, it didn't. It was just some number, and it's log 2. And if you feel where it's coming from, so we computed log 2 to 6 valid digits. It's not a coincidence. Because 6 valid digits means up to error 1 in 1,000,000, and we did it for degree 1,000,000. So there's a bit of a miracle, and this miracle is essentially the big O computation. When I said there's a complexity big O of something, the expected factor in front is log 2, or perhaps 4 like log 2.
What are you averaging?
So I have,
The points, just the points that are converging to.
which most of them do.
Yeah.
Yeah, so here's the disk which contains all the roots, and then here's a circle, and we have k equidistributed points. Some of them might find higher order cycles, will never converge, and of course they will spoil the average. Not many, but it happens. And for all the others, you take the average on how many iterations it will take. And in all cases, and we had a number of experiments, this was a computation of log 2. Yes?
Is the 2 in log 2 the same as the 2 in radius 2?
Exactly. I mean, that you can prove. If it's true for log 2, then here you will get log 3. So because from here to here, the time it takes, that you can compute. But once you start moving further, then it's not so clear. Maybe an indication that the orbits spend most of the time away from the disk. So maybe it's provable, but it was too recent for me to really have time to think about it. But I mean, so far I had only arguments why it could not be independent of the polynomial. But as I said, to 6 digits, it all works. And unlike what we proved, we said we need at least d log squared d starting points, or probabilistically perhaps d log squared. In reality, 4d starting points will find essentially all the roots, and 80 starting points will find them all. We've never seen an example where they wouldn't. So it may in fact be much better. So, and now we we leave the domain of what we can prove and then improve the heuristics. And this is an experiment of a few weeks ago, z squared plus I, where the period is from 11 to 23. So this is just a little table of computing powers of 2. I hope they're correct. This is the number of iterations, Newton iterations that we had to do, times d, which we factored out. And now we take this number divided by d log squared d, and out comes something which seems to converge very neatly. So in other words, you find all, at least for this class of periodic points, you find all the roots with 2.63, I don't know what that number is, times d times log squared d Newton steps, with very convincing numerics, I would say. So, that, you may have been lucky. I mean, so as I said earlier, I mean, his father is listening to me. There are many more experiments one should make, but he's a first-year college student, and you should go and learn his calculus. I didn't want to push him too much into spending all the times on more experiments. So that's the experiments we have. More experiments should be made, but the time we haven't had for it. So in these things here, for a degree a million, the running time was in the minutes, and it doesn't seem to grow much further. And now we were told by some of the professional experts that in practice, the fastest root finding software package is MPSolve. And we had some correspondence with them. They have some sample polynomials on which they work, and we have and some of them were overlapping. And they said they did it up to period, not exactly these polynomials, to period 22, because 23 would take on their high-speed university computer supercluster 5 months. So they haven't even done it. Well, that should correspond to this line here. Well, we don't have an exact comparison between their polynomials and ours. I'm not saying we beat them by a factor of 10,000, but roughly speaking, so, I mean, we are in business, and they seem interested. So I hope to be able to report to you on that, to have the precise results that requires some improvement of the algorithm, to beat them on their demo polynomials, not just something that we invented, it's their demo that we seem to work with. Okay, last slide essentially. Now that we seem to be in business for finding roots of polynomials, that means finitely many roots. What if there are infinitely many roots? So are the transcendental entire functions which have infinitely many roots, they have to have some bound on where there are, for instance, some strip of width 1 that should contain all the roots, and can you make some experiments and develop some theory there? For instance, well, the Riemann zeta function or close forensic C function has the roots in that strip, and that's something that we are planning to work on, and I wish I'll have some results there. And I'm told that some people are interested in finding roots for such functions. And of course, when you want to find roots for a holomorphic function, Newton's method is the method to use, right? Okay, I'm out of time, and I want to thank Jack and Dusa for all their hospitality over the years, Misha and Lilia also. And, well, Jerry and Dawn, who've made it so wonderful here over the years, and to everybody for their attention. Thank you.
So if you are working on a computer, then you don't have exact computation for the sequence. You make errors each time. So if you want precision epsilon in the end, do you know which precision you have to use in the computation?
I can give you various partial answers, and then you draw your own conclusions. One is Newton is error correcting. So you do not have to accumulate accuracy. Errors don't accumulate. So it is okay to compute with low precision initially and then refine as you need. So some other computations you have to sort of think ahead of time how much accuracy you want to have. So that's one thing, it's self-correcting. Secondly, it's hyperbolic, so it's more, at least the dynamics on the immediate basins. So deviations don't matter much. But that is not a precise answer to your question. We have bounds in the paper with Robin that is currently, well, hopefully being accepted, when you can give a precise estimate on how precise you have to compute. But of course, the worst case again is that in every iteration you lose accuracy in one direction and it keeps accumulating, which is unlikely. Even then we have results, I forget the exact bounds. But we have exact bounds for this case. But of course, you would expect that this is more random drift, and then you get a much better estimate. But the method allows you to give a precise at least a bound on how precise you have to compute.
On the slide where you show it took a month, and then a day, and then a few minutes, so what happened in that time? Just the algorithm changed?
What did Robin change? Yes, I mean the whole discussion between Robin and me was that when he wrote his first program, I told him, well, you can't do it that way because the theory tells you have no idea about the theory. And then his response was, well, and you have no idea about the practice. So much of the success is because he did not do what I told him to. And well, I mean, this is with strong young people here. So that was the first program that was very inspiring that we worked in principle. Yeah, I must say it's a bit embarrassing. The improvement from a month to a day was when he discovered that you can ask a compiler to optimize the code. And yeah, so that was that, and that brought it. So I mean, I would have never had the idea to do it. It's just a historical report. So up to here, it is the Newton method essentially as I presented it, except he ignored the constant. I mean, he has some empirical constants. For instance, he doesn't use the d log squared d starting points, but just 4d or sometimes 8d. So he's not following my advice, as I said. But so except for those constants, he was mostly using the machinery from the theory. And then here, this is a bit more free-floating variation on a theme, ignoring more of the theory and just trying to optimize it experimentally. So for the last result, we don't have a theory, we're working on it. But it's sort of past the theory more sort of in the hope, well, let's see what happens if we ignore more of the theory. And it works, well, it works almost, so for these polynomials, now let me be a bit more honest. For these polynomials, it worked perfectly. But for the centers of the Mandelbrot set, the centers of the Mandelbrot set are the sample polynomial from MPSolve 3.0, which is a year old. It's a very recent thing. That example, we used it here too. However, in that case, you find attracting cycles of higher period. And they take a lot of time because iteration never stops. And so they destroy the statistics. And the next thing we have to implement is a stopping criterion when you find higher cycles. That hasn't happened. So it's still, at this point, you see really the quadratic term taking over, which is slow. And therefore, we don't have comparable results for that and with MPSolve. So these are similar, but it's not exactly the same thing.
Any other questions?
Didn't you mention today was your birthday? You've got time, you're going to talk to us instead of, being at home having birthday calls.
Well, my birthday starts in a half hour in Germany. It's not yet.
Well, happy birthday anyway.
Thank you.
Anyone know the birthday song? 1 and 2 and a 3.
Yeah.
English, German.
You have a half hour to practice.
And which birthday is it, Dierk?
Yeah, well, people are celebrating a 25th anniversary. Well, twice 25th isn't so much nicer. Isn't it nicer to celebrate? But it's only in a half hour.
Okay. Happy birthday.
Thank you.